we're going to be talking about work. Um, when we have a system, a thermodynamic system, and we are doing work, we can talk about our system. And I'm going to draw a picture. This is my gas, and I'm going to envision that I have a piston on top of this, and I will push this piston down. Yes, okay. So I'm going to push my piston down. And I have now compressed my gas. I have done work because I exerted a force. My force went down and it changed. It went down to, that's the initial height. That's my final height. And the distance that it traveled is the final height minus the initial height, or negative of that. I've got a change of distance. So my force times my distance that I have traveled is simply equal to the work done, because that's our definition of work, force times distance. All right, so I've got this idea. Now, in our last lesson, we said, okay, so when work is done, that changes the internal energy. And we were able to say, well, the force is the pressure times the area, and times this delta X is equal to my work. And if I use my associative property, area times delta X, then I get work. Well, this is just the volume. So that's pressure times the change of volume is the work done. And we know that pressure times the change of volume from our last lesson, P delta V, is in R delta T, assuming that we are in an enclosed container and the amount of gas isn't changing. We're not leaking or anything like that. And so we now can relate the work done on the gas by an external force to the change of temperature. Coolio. Well, what we have to now think about is our work and how that's actually being done, because we've got two different ways of thinking about it. We will talk about the work done by the gas and the work done on the gas. The work done on the gas, I had to physically push this piston down. It wasn't going to go down by itself. Because that gas was occupying a space, and I had to squeeze it, much like you would squeeze a syringe. Okay, and if you cover the bottom of the syringe like you're washing out a wound or something, then you get a lot of pressure, and eventually you can't move it anymore because liquids are incompressible. So work done on the gas has an external force. And work done by the gas is spontaneous. My gas actually then, if I let go of that piston, it's going to expand naturally. And so this is the gas moves the piston. For the purposes of this course, when we talk about the work done, we are going to talk about the work done on the gas. This is kind of a big deal. It's going to be a sign change. That's what really matters. Because if work is done on the gas, then I am putting energy into the system. I am adding energy to the system. Whereas if work is done by the gas, energy is leaving the system. So what we are going to do is we are going to define work to be negative P delta V. And the reason it's going to be negative is this volume change. Remember, I came up here and I said, oh, it's always the final minus the initial. Well, the final is less than the initial. And so I have to counteract that with that negative sign there. V final is less than V initial. And so then that makes that work being done on the gas a positive number. You will see textbooks that talk about the work done by the gas. And if you move into other areas of science, especially engineering, this sign change may be different. The physics isn't different. It's how we are viewing the world. For instance, it's a relative situation. So for the purposes of this class, we are talking about work being done on the gas, and we will say that the work is negative P delta V. Now, let's go back and look at our first law of thermodynamics that says that the change in internal energy is equal to the heat added plus the work done. Q plus W. So delta U equals Q plus W. That's a new, so we just got two brand new equations. And we haven't really talked about this Q yet. We will be, give us time. And so that delta U, as you know, is 3/2 in our delta T. Q plus W, and that's P delta V. So now we have a way of actually thinking about heat, because heat is now equal to delta U minus W. It's minus the work. So Q is going to be 3/2 in R delta T minus, oh, that should have been a V, minus P delta V. Okay, this isn't so bad. It's not terrible. These are numbers that you can move through. And if you know that, wait a minute, P delta V is nRT. Wow, okay. I forgot the R here as well. Well, we know that PV equals nRT. And R delta T minus just nR delta T, the heat flowing in, you can get a system that looks like that. That's pretty cool. This isn't always quite there, but as you see, this is just a quick derivation. Put this in your notes. The next video is going to talk about different processes and how we define them. And then we're going to talk about diagramming, and we're going to do lots of calculations on this. I will see you in the next video. Okay. We're all in this together.